I was like, yeah, you let Leah have it.
Right, so
You're
we're going to
telling
pay
her
real close attention. Chatty Cathy's, we're going to pay real close attention and look at our
even though so I mean you're gonna all of these
all right, so who has a homework question? I gotta get a homework paper for myself. Who has a question? All right, Julia. If we can't be quiet and focused, we're not going to do this, guys. Julia.
Could you do 9E?
9E. All right, so we've got 5 boys and 7 girls. And teams of 3 be chosen if Susie and Billy cannot be on the team together. Now, there are always multiple ways to do the problem, but I want you to think about something for a second. The only restriction is Susie and Billy cannot be on the team together. How many total teams, no restrictions, how many total teams are possible if I have these kids and I'm picking 3? How many total teams would be possible?
Pick 3 on each team.
Huh?
Okay. No. 4.
Tess? 12C3. Now, this is the total teams. That's no restrictions. 12 kids in the room, choose 3 for the team. Okay? Now, every team is okay except for what? The team that has Susie and Billy both on it. All right, how many Susies do I have? 1. And I want to pick her. How many Billies do I have?
1.
And I'm going to pick him. And I need 1 other person, right? If I'm making a team and I pick Susie and I pick Billy, then I need 1 more person. And where's that person coming from? The other 10 people. So this is the total. This is Susie and Billy on the team. Would everybody agree with that? This guarantees Susie and Billy are on the team. These are the ones I don't want. I don't want Susie and Billy on the same team. So what if I took the total and subtracted the ones with Susie and Billy on the team? Would that leave me with the ones without Susie and Billy on the team? Now, can Susie be on the team? Yep. Can Billy be on the team? Yep. The only requirement is they can't both be on the team. So there we go. Now, your other option is to say, okay, I can build a team with Susie on it. I can build a team with Susie and no Billy. I can build a team with Billy and no Susie, or build a team with neither one, and then add all those possibilities up. It is usually easier to do the total minus what you don't want. That is almost always quicker than doing each individual case to add up. Yes, you have to put that in your calculator and get an answer. Now, I am not going to do that in class every time because it takes too much time. But remember to put this into my calculator. I press 12, math, Bob, NCR 3 equals. And that gives me this number. These can all be typed in together and multiplied. You don't have to do them individually. You can if you want. 1C1 is just 1. So if you don't want to type those in individually, they're just 1s. And then 10C1 is 10. So basically, whatever this number is minus 10 is the answer. Tess? I'm not done with this one yet, Tess. Hang on, 1 second. All right, anybody have an answer to this? I just want to check and make sure. 210 to this whole thing? Yes. 210 different teams that would not have both of them on the team. All right. Number 10. A new customer has to choose from among 3 car models, each of which comes in 4 colors, 5 colors, and with any combination of up to 6 optional accessories. How many different cars can the customer order? Okay, so pretend you're the customer. You're gonna walk in and you have to decide what kind of car you want. You have 3 choices, so that takes care of the cars. You know, like, I don't know, Pontiac. They didn't make Pontiacs anymore. I don't know. Chevys, Buicks, and Fords. Okay? You got 3 choices. So then you've picked your car. Now you have to pick an exterior color, and you have 4 choices for that. So you could pick a Chevy blue, or a Buick red, whatever. And then you have to pick an interior color, so now you got 5 choices for that. And then you have to pick which accessories you want. Like, I don't know, I've never bought any car, so I don't know, like power steering, leather seats, electric windows, I don't know, whatever the options are, okay? And you get to pick up to 6 of those. Okay? So, what if I don't pick any accessories at all? It says I can pick up to 6. What if I don't pick any? Would that take care of it right there? So this is with no accessories at all. I'm not picking any of them. Technically, that would be 6C0. There are 6 options and you are picking 0 of them. That's just 1. 6C0 is 1. All right. What if you pick 1? It'd be 6C1, wouldn't it? All this is the same, but now you're going to choose either power steering, whatever, right? What if you pick 2? And 3, and 4, and 5, and 6? Now, what will I do? This is an answer. What is this, 60? And this one is 360, and I don't know, after this I'm out. Whatever those are. So I'm going to get basically 7 different answers. What do I do with those 7 different answers to find the total number of options available to me? I add them up. I add them up. Okay? Now, I'm getting a little bit ahead of myself, but I'll come back to this in a second, but I want you to look at your next notes.
Is there a quicker way to do this than plugging each one in and find it?
We're going to talk about it right now,
But not choose on this.
that's a surefire way to get the right answer.
To add them all up.
Now, what you can do is, each one of them is going to have a 3 times 4 times 5. So you actually could add all those up and then multiply it by 3 times 4 times 5. That would be an option for you. All right, here's what I want you to do. I want you to look at the notes for 9.2, which is what we're going to do today. And down, it says something right here about Pascal's triangle. I want to look at Pascal's triangle real quick. And we'll talk about it and how we use it and what kinds of problems. But right now, we're just going to look at Pascal's triangle. So we start with a 1 and 1. Each row of the triangle, so make a triangle, and each row starts and ends with a 1. The interior numbers are found by adding the 2 previous above. You may have seen this triangle before. Sometimes it's called the arithmetic triangle. So start and end with a 1, and then add these 2 together, add these 2 together. Start and end with a 1, add these 2, these 2, these 2. I'll do one more, start and end with a 1, add these 2, these 2, these 2, and these 2. You could keep building that forever. Okay? But I want to make 2 observations about this. First of all, let's look at the sum of each row. So the sum of this row is 2. What's the sum of this row? 4. What's the sum of this row? Are you noticing anything? What's the sum of this row? How about this row? Okay, I think you got the hang of it. The sum of each of the rows of Pascal's triangle is 2 to the power, that's the row you're in. So when we added up the 4th row, that was 2 to the 4th. And when we added up the 5th row, that was 2 to the 5th, and it's going to be that way forever. All right, so that's the first observation I want you to make. Now I want you to get your calculator out. And there's 6 rows, so I'm going to do one more row. 1, 6, 15, 20, 15. Oh, actually, I don't. I need 6. All right, so let's go back to the other one, this row right now. Okay? So I want your row, the window row. You guys are going to type into your calculator 6C6. Or, excuse me, no, 5C5. This is the 5th row. The 5th row. 5C5. And I want Chris's row to type 5C4. I just want you to tell me what these numbers are. Allison, your row's got 5C3. Julia, you got 5C2. Sammy, 5C1. And Zoe, 5C0. I want you just to type that in on your calculator and tell me what you observe. What was 5C5?
1.
What was 5C4? 5C3? 5C2, 5C1, and 5C0. So in other words, the row adds up to 2 to the 5th, and the numbers in the row are the combination numbers. So if I went one more, I had them up here and erased them. This row of numbers right here would represent the combination numbers for 6, 6C6, 6C5, 6C4, 6C3, and those numbers would add up to 64. So let's come back to this problem. Did anybody actually work this out all the way and get an answer? Okay, you got it, okay.
3,840.
Hang on to it. Would you take 3 times 4 times 5
Yeah.
times 36, or times 64?
So 60 times
3 times 4 times 5, yeah, times 64.
You get the same answer.
Whoa! So you said to me, is there a shorter way?
That is the shorter way.
There is a shorter way if you recognize that in this problem, you essentially are going to be adding up all the combination numbers for 6,
Right.
which are the 6th row of Pascal's triangle, which add up to 2 to the 6th, yeah. Okay? So, lots of cool observations right there. Hang on. All right, let's back up. Let's do one more homework problem, so someone else raise a hand. We need one more homework problem. We're going to use Pascal's triangle today. But first, okay, Julie already asked one. If I don't see any other hands up, I'm coming back to her. Okay, Liam, which one?
11.
11. How many diagonals does an octagon have? Well, there is a formula for that from geometry, but let's see if we can figure this out if we don't remember the formula. So an octagon has how many sides? So 8 vertices, right? 2. And the diagonals, I have 1, 2, 3, 4, 5, 6, 7, 8. So the diagonals are segments that join non-consecutive vertices, right? This would not be a diagonal. But that would be 1, this would be 1, this would be 1, this would be 1, and so on. Now, basically, I have 8 vertices, and I am joining them, or 8 points, and I'm joining them 2 at a time. 8C2 would represent all of the possible line segments. 8 points, pick 2 at a time, any 2, join 2 at a time. Now this would be all the possible segments, including this one, which I don't want, and this one, which I don't want. So that's the total. How many of them do I not want? 8. I don't want the sides, right? I want every possible joining of the points except for the ones that make the sides. So this will be the answer to the question.
-8.
-8, the sides. HC2 is all the lines. 2 points make a line. So HC2 would be all of them. Subtract out the ones you don't want. And what is that answer? 20. Now, we could probably logic this out. From every vertex, okay, I've drawn in from this, I've drawn the diagonals from this vertex. From every vertex, there can be how many diagonals drawn? 5. So there's 8 vertices, and I can draw 5 diagonals from each one. But if I have already counted this one, I cannot count this one. Agreed? So every one of those is counted twice. So I got to divide by 2, and that will give me my answer. So that's another way to do it. The formula from geometry, and I know for some of you that's been a long time ago, but the formula from geometry says n minus 3 divided by 2. So if there's 8 sides, and that's fine. No one cares how you do this problem. But it fits in this because it can be done with combinations. All right, one more. Somebody else who has a question. Anybody, Lily?
9D.
9D. There needs to be at least 1 boy on the team. So we're back to the 5 boys and 7 girls. Now again, I want you to start thinking about the problem, at least be open to thinking about the problem like I thought about this one. I took the total and took out what I didn't want. Okay, Billy and Susie. That's what I did the first problem I did today. I took the total and pulled out the Billy and Susie teams. So what do I not want? The total number of teams. The total number of teams is 12C3. This is every single possible team. Would you agree with me? Now, which ones do I not want? The ones with no boys. So no boys would mean all girls. Well, I've got 7 of them. That would be the all-girl teams right there. Now, if I take my total, and here's a big bucket full of all the teams, I start pulling out the ones with all girls. What would that leave me with? Who's in the bucket now? Teams with boys. And isn't that what I want? Yeah. Your only other option is to find the number of teams with all boys, the number of teams with 1 boy, and the number of teams with 2 boys. So you can do that and add all those up, and that will give you the right answer, absolutely. I think it's shorter and easier a lot of times to take the total minus what you don't want. All right, does that make sense? You do. You're taking out all the girls. This is all girl teams. So if I take every possible team and pull out the ones that have all girls, no boys, there's no boys in here, what is that going to leave me with? Teams that have boys on them. 1 boy, 2 boys, 3 boys, I don't care. They got boys. Because I'm taking out the possibilities.
Do you have to review 13?
One more, last one. Suppose that a 13-card bridge hand is dealt somewhere in the world every second. How long will it take for every possible hand to be dealt? Well, I need to figure out how many possible hands there are. So, these are 13-card hands. So 52C13 would be the number of hands that are possible, right? So I'm doing 1 a second. All right, it's times 10 to the 11th, right? That's how many hands are possible. That's how many seconds we're talking about. So let's divide that by 60. And that will tell us how many minutes. Let's divide it by 60 again, and that will tell me how many hours. Divide by 24, that'll tell me how many days. Divide by 365, that'll tell me how many years. So it's going to be 20,415.82 years. Okay, so the number of hands is the number of seconds.
Yeah.
Change that into years. So divide by 60 minutes, divide by 60 hours, divide by 24 days, divide by 365 years. Okay? All right. Good stuff. All right, now we're moving on to 9.4, or 9.2, 9.2, one at a time. And at first glance, this is going to seem like it's unrelated. But it's not. These are binomials, x plus y is a binomial. And when we say expand it, we're just taking it to bigger and bigger powers. You take it to the first power, you just get x plus y. But if you square it, what do you get if you square this? You've done it a million times. X squared plus 2xy plus y squared. Now, you also have cubed it, I'm pretty confident, but you haven't done that one as much. But you would cube it by taking this times another one, right? And I'll just write down the answer because I have done it many, many times. You are not responsible for memorizing this. What you are responsible for is beginning to see a pattern. I am not capable of memorizing all that. I'm 64 years old, half my mind is gone. I cannot memorize all of that. There is some kind of pattern happening here. And I want you to tell me what x plus y to the fifth is. That's down there, that's problem number 1. But we have already, you already know what this is going to look like. First of all, do you know what your variables are going to look like? Take a look. What's happening to the powers in the problem?
It's off.
The x's are going, as we go that way, the x's are going down by 1, and the y's are going up by 1. So this is going to be x to the 5th, x to the 4th y, x cubed y squared, x squared y cubed, x y to the 4th, and y to the 5th. Would everybody agree with that in terms of the variables? Now, I want you to look at the coefficients and tell me if you've ever seen them before. The coefficients up here were 1 and 1. Then we went to 1, 2, 1. Then we went to 1, 3, 3, 1. What are those? That's Pascal's triangle. That's Pascal's triangle. The coefficients of the expansion are going to be Pascal's triangle. Since this is the 5th expansion, 5th power, it's going to be the 5th row. Did you write it down when I had it over there? 1, which you don't have to write down. 5, 10, 10, 5, 1. Don't you wish you would have known that back in Algebra 1 when they were making you multiply all that out? Number 2. Now, it's a different binomial, but the concept is exactly the same. All right? So 2x minus y to the 4th. The concept is exactly the same. Okay? Here's the difference. In the stuff I just erased, my binomial was a plane x and a plane y. So all of my terms had a plane x and a plane y. This one is every term is going to have a 2x and a negative y. Okay, here's what it looks like. 4th power. What's the 4th row of Pascal's triangle? 1, 4, 6. Kids, you're supposed to be looking at it. 1, 4, 6, 4, 1 is the 4th row. So there are my coefficients. Now, next to each of those, in the ones I just erased, next to each of these numbers, I had an x and a y, because that's what was in the problem. Now I'm going to have a 2x and a negative y. So every term is going to have a power of 2x and a power of negative y. I'll put plus signs in there to separate the terms. Each of those is an individual term like I had before. And now I simplify. Oh wait, I need my exponents. I need my powers. So what's my power right here on the 2x? The power is going to be 4, and it's going to count down. And then y's do the same thing from the other direction. And notice, within each term, what is the degree? 4, right? Make sure it is, because when anytime you go to the fourth power, your powers should add up to 4 in each individual term. Now I'm ready to simplify. What's anything to the 0? So that disappears. Do you remember from what we had before? The first term didn't have a y in it. It really did, but it was y to the 0, so you didn't see it. So what is my first term? 16x to the 4th. Kids, the entire term, the entire piece of the binomial goes to the 4th power. So it's 16 x to the 4th. Think about FOILing this out 4 times. Wouldn't you have a 2x, 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 2x? Yes. All right, what's here? What's this one now?
Negative 32.
Negative 32 x cubed y. Now it's negative because you have negative 1 to the 1st power times 8 times 4. This is all multiplied. This is not a subtraction. It's all multiplied. All right, what do we have next? 24 x squared y squared. And it's positive because you had negative 1 squared. All right, what's next? Minus 8xy cubed. We're getting the hang of it, perfect. And then again, remember on the end, anything to the 0 is 1, so don't let him confuse you. Your last term is just, yep, done. And there's your expansion. You can expand any binomial that way. Okay? All right, so the good news is, in number 3, we don't want the whole thing. This is the entire expansion. This is the first term, second term, third term, fourth term, fifth term. In problem number 3, our expansion is our binomial is 2x minus 3y. We're taking it to the 6th power. It would look like this. But we only want the 4th term, so that would be like finding this. Now, the 4th term, all the terms, are going to consist of a coefficient. Remember when we went through and wrote down the 14641? What would it be in this problem? Since it's to the 6th power, it would be the 6th row of the triangle, which I think is 1, 6, 15, 20, 15, 6, 1. I think that's it. I had it up there a minute ago. Is that what I had?
Yeah.
Okay. Instead of knowing all those numbers, writing down all those numbers, I only want the 4th one. So my coefficient is 20. It's the only one I want. If I were doing the whole problem, I would write them all down. Next to each of those numbers will be a 2x and a negative 3y, because those are the pieces of the binomial. Right? Now, again, if I were writing out the whole thing, the power on the 2x, right here, the power on the 2x would be 6. 5, 4, 3. So the power on the 2x that I want, because I want the 4th term, and I just counted, 6, 5, 4, 3. And if I put a 3 on that one, then I gotta put a 3 on that one, not because they gotta match, but they gotta add up to 6. And now I do my arithmetic. So 2 to the 3rd is 8, and negative 3 to the 3rd is negative 27. So I have to multiply 20 times 8 times negative 27, negative 4320. Everybody got it?
Yeah.
And it's going to be x to the third, y to the third. And that right there is the fourth term of the entire expansion. Now again, at this moment, you're not seeing a connection other than Pascal's triangle. We're going to do probability this way, believe it or not. Okay? All right, find the third term. Oh, no. Oh, no. Find the third term of x plus 2y to the 20th. Now, why am I a little bit leery of this?
Because finding the
That's
coefficient.
a big power. And finding the coefficient could involve finding the 20th row of Pascal's triangle. That's absolutely, we could do it that way. Okay, wait a second. Back up. What did I have everybody check? Each row checked and noted that the numbers in a row of the triangle are the combination numbers. So the 20th row would be 20C20, 20C19, 20C18. That's the third number. Now you could get it with Pascal's triangle, but it's a lot faster to remember that Pascal's triangle are just the combination numbers. So 20C18 is 190. So my coefficient is 190. The pieces of my binomial are x and 2y. If I were doing the whole thing, in the first term, the power on x would be 20. And then 19, and then 18. And if that one's 18, that one is 2. So I'm going to take 190 times 4, which is 760, x to the 18 y squared, if I did my arithmetic right. Wow, how easy is that? Now, I can't remember, yeah. In the notes, shoot, in the notes by hand, did I only have you do permutations by hand? I did some combinations too. Alright, so let's review that real quick. Let's say we have 8P4. By the way, let's pick a different number. Let's do 8P6. What's the difference between a P and a C?
Didn't you use order matters?
Yeah, if order matters. So in my card problem I did a minute ago where I did 52C13, the order didn't matter. I just needed to pick 13 cards. When I was making a committee from those groups of kids, order didn't matter. I'm just picking. When order matters is if I'm picking a couple of kids and one's going to be president and one's going to be vice president, then order matters, right? Picking her first and him second is different than him first and her second, right? So if I'm picking for a specific job, then order matters. Okay, so in the notes, I talked about how to do this by hand. Obviously, you can type this in on your calculator. But by hand, this is, anybody remember? 8 factorial, yep, over 2 factorial. Because the general formula, I'll use the notation on your calculator, the general formula is this for a permutation problem. For a combination problem, if it were 8C6, that would be 8 factorial over 2 factorial, but it would also be over 6 factorial.
Will the answer have a factorial in it? Do you keep the exclamation mark?
No, not when you work it out.
Okay.
Like, that one's a big number, I'll do this one. If I'm working this out, let me write my general formula. My general formula for combinations is n factorial over n minus r factorial, r factorial. So the formulas are exactly the same, except the combination formula has an extra r factorial in it. To answer Sabrina's question, if I am working this out, I remember that 8 factorial means what?
8, 7.
8, 7, 6, 5, da 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 da. So doesn't everything after here would cancel that? Sabrina?
Yeah. Yeah, I know. So these
And
two
then I
cancel.
still have my 2 factorial in the bottom.
Yep.
2 goes into 8 4 times, so the answer is 28 if I'm doing it by hand. All right, things are always going to cancel out. Now, not as much cancels up here, so that's why I kind of avoided that one. That's going to be a lot of multiplying. But yes, so you get rid of the factorials by writing them out and canceling whatever you can.
But then in our calculator, we're going to use the buttons.
Yes, if you're doing it on your calculator, you just press the button. And it would say, if you typed in 8C6, it's going to say 28.
Where's the exclamation mark?
In the same place as the combinations and permutations are. All right, so number 5 now. This is not a combination problem, but it uses the factorial idea. So let's look at this and see if we can find a counter example. What does that mean, a counter example? Disproves it. So there's going to be some goofball, I guarantee it, that is going to think we can distribute the factorial symbol. You cannot. All right? Counter example. Millions of them. Let's let M be 4 and N be 3. We'll just do that. So if we let M be 4 and N be 3, this would be what? 7 factorial. All right, anybody know what 7 factorial is? Check it out. I think it's 5040. Okay. So if I let M be 4 and N be 3, this side of the equation is 5040. Now what would this side be? 4 factorial plus 3 factorial, which is 24 plus 6. Are those equal?
No.
Factorial does not distribute. Don't even try it. All right, one more. Prove, oh my gosh, doesn't this look frightening? First of all, a new notation here. This right here means this. You see this a lot in some textbooks. The guys who write these books, they have their favorite ways of writing things. This is another combination notation. And the top number is always the first number, which is the number that you have to choose from. And then this is the number that you are actually choosing. Like 8 kids, choose 2. So this is the same as n minus r. This is combination notation written without the C. I just gave you the formula for this, and in fact, I think I used those very letters. What is the formula for the combination of n things taken r at a time? N factorial, n minus r factorial, combinations in the denominator is the difference factorial and that number factorial. That's the formula. So what's this one going to be? N factorial over the difference, which will be n minus r factorial, and then n minus r factorial. So again, your denominator is the difference, so I have to subtract n minus r factorial, and then that number factorial. What is n minus r? What is in that parentheses? That's r, isn't it? So that's just r factorial. Are they the same? Yeah. Now, what's going on here? Some of you may have already kind of figured this out. Let's go back to Pascal's triangle for a minute. Here is the fifth row of Pascal's triangle. Remember, this was 5C5 and 5C4, 5C3, 5C2, 5C1, 5C2. We wrote out the triangle earlier, and I don't know, we didn't talk about it, but did you notice it's symmetric? Did you notice, first of all, we got the ones on each end, but then you see this match right here, and this match right here, and then sometimes there's an odd number right here in the middle, I mean a different number depending on which row you're in, but the triangle is equal on each side, always. So in other words, 5C4 matches 5C1, and 5C3 matches 5C2. That's exactly what this is saying. This is saying if this is 5 and this is 2, then this is going to be, I don't know what I have that in there for, 5 and this is going to be 3. And they always match. My last comment to you is, this is powerful stuff. Last comment. That should make crystal clear sense to you. Think about this for a minute. If there are 5 kids in the room, and I walk in and I choose 2 of them, I walk in and choose 2 of you. Doesn't that, and I take them out in the hall as a group. Okay, you're my group of 2. Doesn't the act of choosing 2 automatically choose 3? Because when I group 2 of you to take out in the hall, I've automatically grouped the other 3 as the unchosen. So 5C3 and 5C2, of course, match. 11 kids in the room. If I pull 4 of them out, that number is going to be the same as what? 11C7. They're going to equal always. Now, not if order matters, then they're different. But in terms of combinations, they match. Oh my gosh, it's mind-blowing. So much to know.